Welcome to the PMPS20 workshop at Supercomputing. Our names are Kristi Allapat and Jan Laukemann, and we are presenting a performance modeling of streaming kernels and sparse matrix vector multiplication on the A64FX CPU. In June 2020, the Japanese Fugaku supercomputer reached number 1 of the top 500 list with an outstanding peak performance of more than 400 petaflops. It's powered by Fujitsu's A64FX SoC and therefore became the first ARM-based system on the top of the list. While Fugaku consists of FX1000 servers, we got the opportunity to investigate the FX700 system that is featuring the same A64FX CPU. Each node is made up of 4 core memory groups enabling non-uniform memory access. Let's have a closer look on a single CMG. 12 CPUs are bundled into one core memory group. They run with a fixed core frequency of 1.8 GHz and support ARM's new SVE instruction set with a maximum vector length of 512 bit that can represent 8 double precision elements. Therefore, we run our tests with GCC 10.1.1 using the corresponding optimization flags as well as -O-fast to exploit SVE vectorization for all presented kernels in this work. Each core has an exclusive L1 cache with a size of 64 KB and a cache line size of 256 bytes. The level 2 cache is shared between all cores of a CMG and has a size of 8 MB with an equal cache line size as the L1. Finally, the shared main memory provides 8 GB of HBM2 memory per CMG. In this figure, you can see the bandwidth using compiler-generated OpenMP code with compact pinning for 3 elementary operations: the stream triad, a sum reduction, and a sparse matrix vector multiplication with a HBCG matrix using the compressed row storage format. All of these should be strongly memory bound, but only triad shows the typical saturation pattern within the first CC-NUMA domain, with a saturation of 210 GB per second for a single CMG and about 800 GB per second for a full node. So why don't we see this for the other two? Looking at the single core bandwidth of each kernel, we can already observe a difference of up to 5x between the codes. Therefore, understanding the single core performance will give us valuable insights into performance bottlenecks of the kernel, as well as this new CPU architecture. To achieve that, we are using the execution cache memory model. It consists of 3 major components. First, the in-core part that is defined as in-core execution and data transfer between the register and the L1 cache. Secondly, the data transfer throughout the memory hierarchies, so in our case L1 and L2 cache and main memory. And lastly, an overlap hypothesis, meaning in which way those data transfers can overlap. Here we can see the simplified in-core model of the A64FX. After instruction decoding, micro-operations get scheduled to the corresponding reservation stations, each with 20 or 10 entries, which is quite a limited number compared to other state-of-the-art server CPUs. After this, micro-ops will be issued to one of 8 pipelines. These differ, in a simpler approach, between floating point operations, integer operations, loads and address generation, and branching. For storing floating point data, pipeline FLA must be utilized. In the table on the right, we are showing the throughput and latency of some of, for this work, relevant SVE assembly instructions. Loads can be executed in pipelines EHEA and EHEB. This possibility of parallel execution explains a measured reciprocal throughput of half a cycle for a standard load. However, gather instructions, which we divide into simple and complex, depending on the stride index used, are a bit more costly and need up to 4 cycles. The SVE store cannot be executed in parallel with loads and require, on top of an HEU, the store port on pipeline FLA. Arithmetic instructions, such as floating point add or FMAs, utilize the floating point pipelines FLA and FLB and can therefore reach a reciprocal throughput of 0.5 cycles at best. Note also the relatively high latency compared to modern competitor CPUs for all the mentioned instructions. This, in combination with the small non-unified reservation stations, can be identified as potential bottleneck and lead to inefficient out-of-order execution, as you can see in later examples. But what does all of this mean for the runtime prediction of a streaming kernel, like the stream triad? Below the high-level code, you can see an excerpt of the corresponding assembly for one SVE iteration. If applying sufficient unrolling, The loop control overhead can be ignored, and the kernel is bound by the steady-state runtime of the loads, FMA, and store in the highlighted box. Mapping this to our port model, the two loads can be executed in one cycle on pipelines EHEA and EHEB. The FMA instruction requires either pipeline FLA or FLB, and the store instruction utilizes VHEUs and pipeline FLA for accessing the store port. As mentioned, it cannot be executed in parallel with a load. Therefore, one SV iteration requires 2 cycles per vector length with optimal out-of-order scheduling. Hence, this kernel is bound by the memory accesses, and we can omit the FMA instruction for further modeling.
Once we understand the INCO contribution of ECM model, next we look into an important component of the model, that is the data transfer time between the caches and main memory. The FX700 system is capable of loading data from L2 to L1 at a rate of 64 bytes per cycle, and storing back at half the bandwidth, that is 32 bytes per cycle. Similarly, the load and store bandwidth between main memory and L2 cache is 117 bytes per cycle and 64 bytes per cycle respectively, which are relatively high values compared to modern CPUs. Knowing the machine's capability or rate at which we can transfer data between caches and memory, the only thing left to estimate the runtime contribution is the knowledge on how much data have to be transferred between the caches and main memory. This is where the application or code comes into the model. For the stream triad example, we need one load corresponding to array B, one load corresponding to array C, and one load corresponding to the write allocate for array A, and finally a store for array A. This means we need 3 loads throughout the memory hierarchy and 3 loads between L2 to L1 at a rate of 64 bytes per cycle, resulting in 3 cycles per vector length. Using the same principle, the rest of the load store contributions can be determined. Now, these data traffic contributions have to be combined with the INCO predictions made earlier. And the important question is, how do these contributions, which are represented by boxes here, overlap? So we have to test different overlap hypotheses. It could be that none of these contributions actually overlap like the current Intel architectures, or all of them overlap like the current AMD Zen 2 architecture, or it could be anything in between. There are numerous possibilities. Naturally, more the overlap, lesser the runtime, and therefore better the single core performance. From these numerous possibilities, how do we find the appropriate overlap hypothesis for a given mission? For this, we have to compare the measurements with predictions for several kernels with different flavors of load store pattern and caching properties. It turns out that for FX700, the best overlap hypothesis is the one shown in the figure. From this figure, we can read the ECM model prediction for different cache levels. For example, when the data fits in L1 cache, the ECM model predicts 2 cycles per vector length. And if the data was in L2 cache, the model predicts 6 cycles per vector length, and 7.7 cycles per vector length if the data was in main memory. If we now compare the predictions to the measurements, we see that the predictions lie very close to the measurements for this particular hypothesis. However, when carrying out the measurements, we have to take due care, especially on the FX700 system. The unrolling factor, for example, plays a critical role. Even with slightly more complicated kernel like the 2D 5-point stencil seen on the left figure, the difference between the unrolled version, that is the blue line, and the non-unrolled version, the black line, can be as high as 50%. This is basically due to the inefficiencies in the out-of-order execution, which was mentioned earlier. The sum reduction benchmark, on the other hand, suffers more than 3x performance drops if not unrolled. For non-unrolled version, the bottleneck is the add pipeline latency, which on this system is as high as 9 cycles. This dependency on the add pipeline can, however, be resolved if we do proper unrolling using modulo variable expansion. For this code, the GCC compiler does vectorization, but unfortunately does not do proper unrolling to hide the large latency of the add pipeline, and therefore this has to be done manually. Understanding the ECM model, now we can have a closer look into the sparse matrix vector algorithm, so-called SPMV. The SPMV algorithm performs a multiplication of a sparse matrix with a vector X and stores its result in vector B. There are lots of data storage formats that have been proposed. However, the most standard format for CPUs is the compressed row storage format. In this format, we process the matrix vector multiplication row by row as seen in this illustration. Basically, at each row, we perform a dot product between the non-zero entries of that row of the matrix and the vector X, which by the way has the similar dependency problem like the sum reduction benchmark. From the illustration, we can also see that there are some indirect addressing required at the right-hand side vector X. Below, we see the corresponding pseudocode for the CRS storage format. The GCC compiler produces a decent SVE vectorized code, as can be seen from the assembly instructions here. But with this code, we are not able to saturate the main memory bandwidth as seen in the rightmost figure for the HPCG metrics. The main reason for this is that, similar to sum reduction, the innermost loop has a dependency on FMA instruction, which has a high latency, about 9 cycles on this system. Also, the final horizontal add outside the loop is expensive and costs about 11.5 cycles. To make the matters worse, the inner loop length of general sparse matrices are really short. For example, in case of HPCG, it's just 27. This leads to high overheads and inabilities to unroll the innermost loop. With these three facts, it can be shown that with this CRS format, we cannot saturate the main memory bandwidth of FX700. This is why we looked into a vector-friendly format called CELSI Sigma, which is commonly used on GPUs and vector machines. With this format, we store chunk of consecutive rows in column major format. The chunk size indicated by C is tunable and along the very long row dimension. Therefore, with appropriate chunk size, we can have both efficient vectorization and unrolling for pipelining, which hides the long latency of FMA instruction. Also, another added benefit is that with this format, the costly horizontal add can be avoided. Here we see the ECM prediction for HPCG metrics with CELSI Sigma format. Load from L1 to register takes 20 cycles per vector length, and most of this is due to the gather instruction required to indirectly access the right-hand side vector X. The contribution of store is almost negligible. Down the hierarchy, we would further need almost 6 cycles to transfer data between L2 and L1, and 3 cycles to transfer data between memory and L2, which, together with the overlap hypothesis, gives us almost 29 cycles per vector length. This directly translates to a performance of 3.4 gigaflops per second, that is equivalent to 22 gigabytes per second. So this is our single core prediction. And for multi-core scaling, ECM model assumes that the performance scales linearly until it hits the memory bandwidth saturation. This prediction is seen in the rightmost figure. Now, if we do the measurements, we can see that it lies very close to the prediction. However, it should be noted that the machine requires almost all the cores to saturate the main memory bandwidth. Therefore, the performance will be sensitive to load imbalances or any inefficiencies in data access. In comparison to CRS storage format, we see that the single core performance has been boosted by a factor of more than 2 times. And this finally allows us to saturate the main memory bandwidth at about 200 gigabytes per second. This corresponds to almost 30 gigaflops per second. Outside a CMG, which is a single NUMA domain of this system, the code should scale perfectly, and thereby with 4 CMGs we should attain 4 times 30 gigaflops per second, that is 120 gigaflops per second, and which we actually achieve as seen in this figure. Now here you see that the performance on some matrices from the publicly available suite sparse matrix collection. And on all of these matrices, the FX700 system is able to saturate the main memory bandwidth. and it attains a final performance of well above 100 gigaflops per second, which is on the level of NVIDIA V100 GPUs and NEC Subasa vector accelerators. In conclusion, we see that high single-core performance is crucial to saturate the high memory bandwidth. ECM model was thus established as a tool to understand and analyze the single-core performance. Through ECM modeling, we found out that the memory hierarchies partially overlap, leading to high single-core memory bandwidth. However, proper single-core optimizations like loop unrolling and others have to be done to hide long floating point latencies and inefficiencies in out-of-order execution. For SPMV, we were able to show that CRS wouldn't saturate the main memory bandwidth, and we need to use other alternatives like CELSI Sigma format. This concludes the presentation, and we are available for questions. Thank you.